Hello to viewers, welcome to my channel Science and Technology. In today's show, Rocket Monday, we're going to talk about long lead items. What the hell does that mean? So let's dive deep into it. So fundamentally, you have to understand that rocket company does not need anything that you can just buy, like flat out. You might think, oh, it's industrial and this is like reality is when you actually open a rocket company is that, yeah, none of the item is what we classify as industrial, common or off the shelf. None of it. Like fundamentally, it's on such a different level that there are many companies. In India, there are many private space companies. In China, there are many of them. In America, there are many. How many of them actually manage to reach orbit? That number shrinks. Why? This is one of the very critical items. If you are just starting out, you will have no idea how long these things can take. And here's the deal. Money cannot buy time. Like flat out, no matter who you are, it does not matter Elon Musk or Jeff Bezos, you do not have enough money to buy time. None of them can. So mismanagement leads to what we call cascading delay, so to say. As in, imagine a world which happened in 2021. SpaceX bids for human landing system and they're like, yeah, we're gonna deliver this puppy. 2023, 2024 is worst. Okay, cool. 1 year passes. Only in 1 year, NASA can figure out, yeah, that's not happening. That's not happening, not even by 2030. So they will open the contract and start giving the money to someone else. Why? There are long lead items. If you study it properly, you can figure out who is gonna get done and what's not going to get done. No matter who you are, it does not matter, flat out. There is cascading delay factor to it. Like Elon Musk was landing on Mars in 2020. Almost people forgot about that. And 2024 moon. I'm like, it's how it will be 2030 to low Earth orbit. So fundamentally, cascading delay is a big issue. And there is a lot of red tape whenever you're talking about rocket. This is a very big destroyer of startups. They have, again, you do not expect that, but you have to understand this. Rockets are just ICBM bigger brother. So you take ICBM, you expand it, that's orbital class rocket. So fundamentally, it has to have this sort of red tape and constraint. It's a good thing. It's a necessary thing. But it does come with a penalty. For example, you can be like, hey, rocket happened and boom happened and I want to try again. FAA says no. That means no. The end. The end. There is no discussion after that. That's why all the private space company were directly targeting Congress. Is like, bro, change this rule. Again, if there are no humans involved, that's kind of acceptable. But you can understand there is a lot of paperwork and bureaucracy and it has to be there. So you can't rush that. An irreplaceable timeline vulnerability, as in if one part fails, yeah, the whole clocks could reset for years. For example, the worst case scenario was SLS. Like the delay on this thing is hilarious. It's not even bad. It's just hilarious. Have a laugh at it. Like how the heck you could be delayed by decades, so to say. So there is fundamental reality to this. So first vector that most people have to understand is cryogenics. This is what Jeff Bezos was talking about. Thankfully, that was not destroyed, as in cryogenic farm. So rocket industry is thirsty for cryogenics. Not only it uses generally the lowest temperature liquids, the amount is bonkers. To give you a context, there are many industries that consume cryogenics. Like for example, your hospital consumes liquid helium for MRI machines. And there are other systems also, including oxygen, liquid oxygen also for storage and patients and all that. So there are a lot of industry, and metal industry, they drink cryogenic like there is no tomorrow. Here's the compare their consumption to a rocket. Yeah, rocket is like, bro, no. Like it's a months of consumption versus 7 minutes. Like this sort of truck, trying to refill a oxygen tank for NASA launch. Yeah, this truck can like few factories like, bro, chill. I got this. I have enough. Like I have enough. This tanker is like cute. Send hundreds more. So the scale is bonkers. Like you cannot just open your mouth. It's like, hey, does anybody know how to make ginormous cryogenic tank that can handle liquid hydrogen? Yeah, the answer is no. No. Like nobody. Even LNG is not that cold. So fundamentally, and the scale, when you are talking about the size, you want to make ball tanks. Now, why ball tanks? Because again, physics likes this. It's what we call surface area to volume ratio. Meaning, if you put a liquid hydrogen into this, for how long it can maintain it, it would be the best, flat out. Why? The surface area is so low. The liter is high and cubic meter is very high, and square meter surface area is very low. So it fundamentally cannot radiate heat away, meaning once you fuel it up with tankers, it can run for a very long time. I'm like, wait a minute, then why the heck SpaceX does not do it? They had a choice to make. Again, I'm reasonably sure, or more than enough engineer would have told, like, we should build a giant tank. It's just that making that giant tank could take months or a year. So they are like, okay, just use a bigger version of these sort of tanks, cryogenic tanks that are industrial grade, and you can just pick up a phone and order it. What's the penalty? They will boil off, meaning instead of consuming 10 trucks, they're gonna consume 11 trucks. That sort of deal will happen. But again, I think they made a sense where it's like, it makes sense. But there is a reason why every traditional rocket company generally invest into this. And for launch cadence of NASA's point of view, this is fine. And they are big enough, they are low loss enough that they can handle, like, few launches. So storage, custom, everything is custom. The piping, the valve, the welding, everything is custom. And when it comes to valve and plumbing for this thing, and I'm talking things that are on ground, yeah, there is only few things that can come close to it. For example, how much is the flow rate when you're draining this ball tank? Yeah, give or take city pumping level, meaning you have city as water mains. This could have higher flow than that. I'm like, okay, then just use that pump. Yeah, that would be fine if this was not cryogenic. At cryogenic, this becomes no. So that allows you, like, basically you have to have plumbing that is strong enough to tank a city and still be robust enough to handle almost 0 Kelvin. Yeah. And how many companies, OEMs, have the ability to make valves that work at this sort of serious loading? Yeah, few. Like, there are certain technologies, does not matter how much money you have, does not matter how much demand is there. It's just not there. Same thing is here. For example, ASML. No matter how much money China puts on, no matter how much money every Tom, Dick and Harry puts, there is only one ASML. Same thing. It's like, no matter how much money somebody is willing to, like, the cryogenic that can work for rocket industry, that's a very small group of companies that can handle that. Very small. It's almost like a black magic of a single crystal blade. Like, they can tell you, this is how we are making single crystal blade. Good luck trying to replicate it. Like, they will tell you, like, yeah, this is what we are doing. Good luck. You will not be able to replicate it. It's a black magic class technology. So cryogenic is brutal. So if these things get kaputted, yeah, it's going to take a time. Does not matter who you are, what you are, how much money you have. Does not matter. Then we come to the brain aspect of it. And again, now we are going into space. So you can use, let that be very clear, you can use off-the-shelf microcontrollers, electronics, op-amps, whatever have you, but they will not meet the reliability standard. For example, when a student is launching a CubeSat, if CubeSat works, great. If it does not work, no big deal. That's the whole essence of CubeSat. But if NASA launches it, it's like, yeah, no. It has to work. It has to have the 6-9 probabilities of working, as in like 99.999999 probability of working. So when you need to have that sort of demand, and why do you need that? If you want it to work. Basically, if a CubeSat goes kaput, who cares? If James Webb Space Telescope goes kaput, everybody cares. So that's the whole point. Serious lifespan, that's the critical thing. Do you want it to work for 1000 hours, or do you want it to work for decades and decades? Like, do you want it to be long lasting as Voyager? If you want it to be long lasting as Voyager, then the whole ball game is different. So you have to have what we call a rad hardened, a radiation hardened, and a TIT, total ionic doses, so to say. As in, radiation creates damage in your body. Fun fact, it does that on solids also. So if an IC, let's say ICBM IC, it's only supposed to handle deep space for a few minutes. So they will test it for 100 hours. But if you're talking about any probe that is going to, let's say, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, those sort of distance, like deep space, outside of Earth's magnetoshield, over time radiation will fry it. So you have to have that very good TIT. And many of these hardware, after building, has fixed duration path. As in, oh, you built it, cool, now test it. How long it will take? Yeah, few months, or some cases, year. Not even joking, there are certain lead items. Again, you will not do it for everyone, but the corporation that is building the new IC, they will. So, accelerated aging testing, like if you really want to make sure that your microcontroller can handle the Hubble telescope for decades, yeah, you better test the damn thing. So again, accelerated aging does not mean like you can compress, let's say, 30 years in 3 days. It still means months or sometimes year of testing. So, and these are not mass produced. Why? Well, generally they use bonkers amount of gold. Solder is also made out of something different, so it does not degrade or has any malfunction. And they cannot package in that black stuff that you and I see. So generally they are packaged in ceramics. Yeah, these things are too expensive. Fundamentally, gold is too expensive. The unique solder item used, those are also expensive. And the casing, That's also expensive, even if the die is exactly the same. So fundamentally, yeah, you have to pay for it. And due to lack of mass production, they are bonkersly expensive. Like military hardware item and space rated hardware, yeah, they are expensive. So, and after that, it's not done. After that, you do binning. As in, once you have, let's say you figured out this is the op amp that we're gonna use for our instrument. Cool, awesome, GG. Yeah, make 10, 20 of these and then test all of them and select the best one. That's binning. And if you're like, wait, that sounds slow. Yeah, it is. It is. Again, that's how you achieve that 6.9. And that's just the hardware. That's like just the silicon. Wiring harness. Yeah, these are built almost like an art piece. And I'm not joking, they are actually tied by hand still to this day, wire wound, because you have to understand there is a lot of twisting in a satellite bus, so to say, because one side could be hot, other side could be freezing cold, and God help you if you have thruster. So all of these causes torques into your system. There's a lot of thermal motion. Again, it's not moving like this, but it is moving. Over time, day one, nothing will happen, but you have to understand that if you are in low Earth orbit, you could be going in the shadow and night 22 times every day in 24 hours. So there's enough expansion contraction. If your wires were not constrained properly, some will break loose, some will cause short circuit and kaput your mission. So all of these wire, they are wound for this exact reason. They cannot shake around. And again, this also allows them to handle rocket launch itself. Space is brutal, but rocket launch itself is very sharp. So they have to make sure that this puppy can survive, that 140 decibels of shock. So all of this wire harness alone, unless you're making same thing thousands of times and you milled a jig for it, yeah, these things are painful, painfully slow. But again, the benefit is that's how NASA can claim it. Yeah, we had a rover that's supposed to work for 2 years, it's working for 20 years. It can be done. That's how basically Voyager, it's yeah, it should have survived, and it's yeah, we got this. It's one light day far. We can talk in days. That's how far it is. It's one light day. Moon is one light second, to give you a context. So, but again, that you have to go through this process. Only then you can guarantee that, not even guarantee, there is no absolute, but high probability that it will work. Then we come to the muscles part of it. So many things in space have to physically act. It's not just throw a CubeSat. Many of them have to deploy solar panels. This is a big hassle. Then you have covers on optics and all that. That has to be opened. Radio antenna has to be deployed. Dish has to be deployed. And spinning gyroscopes, gimbling thrusters. So yeah, over time, these things start to pile up. Your rocket assembly becomes complex. And penalty of that is we have to do testing again, which is cold welding. Why? When you are talking about, even NASA messed it up. They had this puppy as everything is nice, everything is dandy. They're we're gonna launch it, we can deploy it. Okay, cool. Deploy the high gain antenna. Nothing happened. Deploy the goddamn high gain antenna. Nothing happened. Thankfully, the low gain antenna was functional. So yeah, we kaputted this mission because of that. It did work, but it was working like this rather than both highs. Without high gain antenna, they did not have enough data bandwidth. And what happened? Metal open, the flower spring that's supposed to open, it touched another metal. Metal touching. If the both metal are of the same alloy, when they touch, electron can jump from one to another and cause what we call a spot cold welding. It welds. At that point, a crystal has jumped into from one to another. It is welded. It's the end. It's a permanent marriage. There won't be any divorce of that. So yeah, more than enough missions have learned this the hard way, that for example, hey, I have a hinge, I'm just gonna use aluminum and aluminum. No. You have to have some sacrificial material. Generally they use Teflon, but you have to have something. Otherwise, if these two metals are there and they're exposed to deep vacuum, there is a very serious risk that when you deploy the spring, it's nope, what happened? Yeah, it's welded now. So cold welding. Again, how do you know? We've gone through it. You have to test every single hinge joint and all that. And thermal binding is the nightmare scenario for every company. They have to deal with this. It's okay, what happens if one side heats up? What happens when one side cools down? That's why generally spacecraft have so much insulation. They don't want to deal with this. They're dude, you can't deal with this, just insulate the hell out of it. Then space becomes a constraint, but they do their best. Because again, and God help you, if you have hypergolic thrusters, Those trusses could be hundreds of degrees Celsius, and radiatively you're still getting bombarded by that much thermal radiation. So you will be cooking on thruster side, and the shadow side could be minus 200 degrees Celsius. Yeah, you're literally bending the whole structure. And these are what we classify as single point failure, meaning what happens if your computer fries? Generally, most of these systems have 3 computers. So if one computer goes bad, both can outvote it and still maintain the service. Solar panel malfunctions, the end. Mission equals the end. So they generally go through slow qualification, meaning every screw, every fastener, every rivet has to be checked, validated, everything multiple times, and they have to open and close to make sure that it's at no point it's coming close to something that is not supposed to. For example, if you look into ISS live stream, you will see astronauts are touching metals and all. It looks like metal, here still they are differential metal, as in one metal is aluminum, another is steel, or it's one alloy of aluminum, another alloy, or it has coatings. Otherwise it will not work. So all of these things will take time. No matter what you do, it will take time. Now we come to the most gut-wrenching part, which is validation. Because launch environment is very violent, like 120 decibel is nothing at that point in time. And again, we are not talking sound, we are talking shock waves. So almost 150 decibel. So yeah, these are violent few minutes. On top of that, space is brutal. So rocket breaks you instantaneously, space slowly breaks you. So we have to do our best to test everything. So first thing is acoustic and vibration testing. You put it on a shaker and you go to it. And James Webb Space Telescope had a bolt falling out. So it does have to handle this. Now again, does rocket shake this much? No, but it does go through some period where it is vibrating when it's pushing through max Q, when it's the rocket gimbals are like trying to its best to, sometimes the oscillations could be there. This is the best way to validate it. Like if this can survive the shake table, rocket ride should be minor inconvenience. And that's why we overdo this, because if it can survive this. And after that we have TVAC, that's the final crucible, so to say. So thermal vacuum testing. You put your system into this puppy and you cook from one side while freezing from the other. And yes, they have like lamps, arc lamps, or like not arc lamps, I would say like very powerful IR source. And the other side, they have very powerful radiator that is being cooled down, sometimes even with liquid nitrogen. Like why? Well, photons have to go somewhere, na? So you are, because the chamber is a vacuum, you are cooking one side, you are freezing the other side. So meaning that if satellite launches photons, most photons will bounce around in the shell. So they have to have a sink. The sink is the radiator that has maybe liquid nitrogen or maybe helium going through it, so it can absorb all the photons. So one side is cold, one side is hot, and that's how you figure out whether your twisting can be handled or not. So yeah, that's a painful thing. And again, that's the core difference. NASA will do this thoroughly for the, all of their CubeSat, while a CubeSat launched by a private company is like, okay, test the core principle. If it works, throw like, you know, the test one, throw 9 behind it. That would be the deal. So far, these things are far more mechanical, far more brutal, but then you have the naughty part. Yeah, that is EMI and EMC shielding scan. Yeah, this thing will take time. Like you sit down like this, you can see, you can rush it. Like it's like, I'm gonna be here, we're gonna have multiple techs working one after the another, and we're gonna get through all of that, validate it. This you can rush almost. This put and forget. Yeah, they have to run all the scans, as in all the wavelength, because if let's say you are in low Earth orbit, there are thousands of other satellites that are screaming. How the heck you will make sure that all of your encryption, encoding, basically phasing, everything that you are doing with your radio waves, A, it's working, B, not getting overridden by something else. This has to go into this lab and then you forget about it for a few days or months. So these validations, again, no matter what you do, you cannot rush this. It will take time. See, the only solution is back in the day, like in around the 60s and 70s, satellites were so expensive, they never made one. They were always like, hey, we are making one. Once they figured out how to make that one, they will always budget for 2. Make one, learn everything, make second one. If rocket launch happened successfully, cool, you had one, it worked. If it did not, we had a second satellite. Or day one, because again, if you have to start again after rocket went to boom, yeah, you will go kaput. So this was my presentation on basically this whole idea of long lead items, why there are so many long lead items in the rocket systems. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me disappointment. Please leave a comment because I do try to reply to all of them. And again, if you really enjoyed it, click the like button. Subscribe, press the bell icon if you're free, and as always, thanks for watching.